Okay, now in this video, I'm going to show you how these 41 gauge coils run with this capacitor bank, but if I put the same amount of resistance that there is in these coils, which has half a mega ohm, or around 480, 490, so 400, let's say 490 kilo ohms of resistance between all 6 coils of 41 gauge wire, and it can power, this capacitor bank can run the motor with torque. So now I'll show you the motor running on this capacitor bank. Let's not do that quite yet. I need to switch this wire around to here. Alright, now put this on there. It's got to be careful. I don't like playing around with high voltage. So, gotta change this back to volts. DC. Alright, so we're at 220 volts. And I'll get it started. And we're running on that capacitor bank at 200 volts right now. And to show that there is torque, as soon as it gets to that point, it'll push the magnets. So that's with the 41 gauge coils, all 6, top and bottom, still at that voltage. I'm going to charge the capacitor bank up a little bit so to get it back to where we started before. Alright, that's good. Alright, now I'm going to switch over to the 10 gauge coils, and now I'm going to drop the resistance going into them with a 470 kilo ohm resistor. I'll show you, I'll measure it. So the resistance on this is quite high. Come on. Why is it being so difficult? Alright. So we have, if this thing would cooperate. Oh my god. Alright, let's try this. Or not. Sorry guys. Okay. There. So now the resistance in this resistor is pretty close to the coil output resistance. So around 490, 500 again. So that's, let's say a 500, it's not a 500 ohm resistor, but it's like a 480 ohm resistor. But now I'm going to try and do the same thing, but run these coils with the same amount of resistance as these. Alright, let's unhook that, so we don't need that lead anymore. Let me guess, the voltage is probably lower now, but not that it's really a big deal. It really isn't. Not for this demonstration anyway. No, we're pretty close to 200. Close enough for me. Alright, now I will swap this over to the thick 10 gauge coils. And we will put this on here. Let's show the voltage drop. Alright. So we will put the resistor on I might have to swap this around. I don't know. I don't think so though. Either way. Come on. Right, now it would look like this. Will that help me? Alright, so never mind. Come on. Wow, is this thing being difficult? Alright, now it's connected, I believe. Let's see. Let's see what happens. Alright, yeah, it's connected. It's taking power from it. But it cannot run the motor at all. Literally, it cannot run it. Oops, that was my chair. That's my bad. But, there is absolutely no torque. It can't even run the motor because there's not enough magnetic field generated, obviously, to turn the motor, but yet these have the same amount of resistance as this one resistor here, but it can run the motor with torque. So there's the same amount of electrons flowing through the coils, but yet this one still produces a stronger net magnetic field than the 10 gauge coil, because there's I think like if a garden hose was, say a ½ inch versus a garden hose, not that it would make a garden hose that thin, but an 1/8 inch, it would take there's more resistance in the 1/8 inch one than the quarter or the half one. So in theory, there should be the same amount of electrons flowing between the two different coils, but there's higher resistance than this one. So I'm not really sure what the outcome is on this, why this one would produce a stronger magnetic field. And I think it's because I'm not choking it down with a resistor, where the energy is lost in the resistor versus the coil. So as this is bleeding down, sitting there, not powering the motor but still drawing power, all the power is going to the resistor versus generating a magnetic field in the coil. So this is kind of a bad comparison, but at the same time, I'm just showing you that the amount of resistance in this coil can't power the same amount of resistance in a thicker gauge coil. This is a pretty dramatic comparison. This is 10 gauge versus 41. This is pretty thick coils, so. But what I'm trying to get at here is I'm still able to run a motor at that resistance level with torque and able to run it off of a small capacitor bank for quite some time, which is awesome, but at the same time it's very, very difficult to switch high voltage at higher, like once I get this thing up to speed, it's nearly impossible to switch the voltage to these coils because there's just a problem with arcing. And I need to figure that out. Yeah, I know there's flyback circuits, but we're talking like tens of thousands of volts. Like that's a lot, that's substantial. So what I might do to step down the voltages is I might run all the coils in parallel, or run all these in parallel and the opposite side in parallel, and then junction those two together to, help reduce the amount of resistance. But my point was trying to power a motor and make it most efficient as possible. These coils actually run amazing. Actually, they run down to like 0.1 volt or 100 millivolts. It can still run the motor with torque, but it takes a lot of current. So I believe that once I get a multimeter that can measure current, I'm going to take the difference of current draw from the 10 gauge coils, and at its lowest running state of 0.1 volts or 100 milliamps or millivolts versus the minimum requirement on the 41 gauge coils, to see the current difference and the power consumption between the two. I am having a theory that the 41 gauge should be a lot less power consumption versus the 10 gauge coils at their lowest state versus these lowest state. So that's my next step. Other than the fact I need to get the switching mechanism working. And I'm going to have to run with this one for now. It worked pretty decent. I'm going to probably switch out the copper for the graphite foil. It's easier to make too. And I could get the timing a little better. It's not perfect. It's pretty close to perfect, but it's not perfect. So yeah, that'll be my next steps. Alright, this video's getting long, sorry.